So, welcome to all of you in lecture 13. This is from the topic work and heat transfer. So, today we discuss regarding some other important aspects. The first one, that is a free expansion. So, question be raised here that what is free expansion? Okay. So, for understanding this concept, we have to move towards our board. Yes. So, free expansion meaning that is something expansion which is without any restriction. Okay, suppose if we take a well insulated chamber like that. Okay, this is well insulated chamber, and we divide this chamber into two subsections. Okay, this is first section and this is second, and these two sections are divided through this separating wall. Okay, so what will happen if we feed a gas A inside the chamber first, okay, and chamber 2 is in the state of vacuum. Okay, section 2 is in the state of vacuum. So what will happen if we remove this separating wall from this insulating chamber? Then this gas is trying to expand in throughout the vessel. So if we plot pressure volume curve for this event, what event? This gas trying to expand in throughout this insulating chamber. So if we draw this event in PV diagram, we get this is the initial state when this gas is filled inside first chamber, and this is the second state when this gas is totally covered throughout the space of this insulating wall. Okay, so we can say that if we define second state volume, that is equal to V1 subsection volume plus V2 subsection volume. Okay, this is the summation of individual volumes, first and second. Okay, this is the second state. The problem is that if we want to relate these two states through a path 1 to 2, then the problem is that this expansion process is too much fast, and that's why we cannot do any type of command for in which manner this process is happening, like that, or like that, because as we remove this separating wall, all the gas all the gas molecules in a very fast manner cover throughout the volume of this vessel. That's why we cannot define the path between these two first and second stages. So for such type of system, we connect these two stages, initial and final stages, through a dotted line like that. This is the second state and this is the first state. So if we trying to connect these two states, so we draw a dotted line path between these two states. We draw this dotted line path because we cannot define the actual path between these two states. Okay, because this process is happening in a very fast manner. And if we want to define, in a previous lecture, we already discussed that if we want to define a clear and exact path between two states, then we have to search lots of equilibrium states between these initial and final states. And that's why such type of process in which path is actually defined, that process are known as quasi-static process. So if we want to calculate work done for such type of process, so we already discussed this expression PdV, W equals to integration of PdV, where stage is changing from first to second. But this process is only valid for quasi-static processes. That means process must be performed in a very slow manner. So still we know initial pressure and volume condition when this gas is filled only in a first chamber, and we also know second condition when this gas is entirely filled in throughout the chamber, what is the pressure and volume value. But still we cannot calculate work done with this expression because this expression is valid only for quasi-static process. And such type of process in which free expansion is taking place, this expansion is taking place against the vacuum. So such type of process are happening in a very fast manner. So we cannot calculate work done to this parent expansion integration of PdV. Okay, got my point? Another important aspect is that this gas is expanding against the vacuum. So there is no resistance is offering against the expansion of gas. Okay, so we know that if we talk about work done, maybe it work done by the system or work done on the system, then there is something which is against the, which is resistance, which is offering resistance against the deformation. So in such type of events in which resistance is happening against the motion, then work done is adjusting. But in this case, there is no element which offering resistance against the expansion of this gas, because in a second subsection there is vacuum. So such type of process in which there is no body which offering resistance against the expansion of gas, that is the example of free expansion. That's why we tell this term as a expansion which happening in a free manner. So if we talk about work done in a free expansion process, that must be equal to 0, because there is no element which offering resistance against the expansion of gas. Okay, so that's all about free expansion. Now we move towards our slide. Yes. So what is free expansion? So this is, let us consider a gas separated from the vacuum by a partition. If the partition is removed, the gas rushes to fill the entire volume. The expansion of gas against vacuum is called free expansion. And the second one, there is no work transfer involved here, since no work crosses the system boundary, and hence integration of 1 to 2 dW, that is equal to 0, although integration of 1 to 2 PdV that does not equal to 0. Here, all the expansion process is happening inside this chamber. And if we talk about boundary is like that, in which we put insulating layer over that. Okay, so what is happening in this problem? All gas expanded inside the boundary, and in a very first lecture, we already discussed that work and heat both are boundary phenomena. That means work and heat both must be transferred through the boundary interface. But here expansion process is happening, but work cannot cross the boundary interface. So that's why we can say that integration of 1 to 2 dW that is equal to 0, because work is not crossing the boundary. And another thing which make it 0, that is nothing here present to produce resistance against the expansion of gas. That's why this expansion is 0. This is the another reason for this expansion 0. Okay. Another important is that if we try to expand this gas in separate partition. Okay, I'm trying to show you on board. Okay, see that. And previously, I am telling you that we cannot define actual path between these two states, first and second, because this process is happening in a very fast manner. Okay, so if we see again this chamber, this is insulating layer. Okay, this is a separating wall. Here gas is filled, and this is a vacuum. Okay, in the first case, we just remove the separating wall and permit this gas to expand in a throughout chamber. But now, in second case, if we slowly shifted this separating wall, in a first condition that is that, in a second condition, we slightly shift this separating wall here. Okay. In a third condition, then we again shift this separating wall here. Okay. In a fourth condition, again we shift this separating wall here. So like that, if we slowly shifted this separating wall towards right hand, then we get in a mid manner equilibrium conditions. Okay, like that. So what happening in this case? Now you have some intermediate equilibrium states between initial and final position. And by connecting these intermediate states, we get actual path of expansion process which is happening in this system. So what happened? Now you can say, yes, we can apply this expansion W equals to integration of 1 to 2 PdV, because we process this path in a very slow manner. But is this work existing? The question is that no, still work is not happening in this example, because another important term is that work must be done against any resistance. But in this case, we provide some intermediate stages between initial and final stages, but this gas is expanding against the vacuum. So there is no resistance. So we get these intermediate stages. We can use this expansion, but the another fact is that since this expansion against the vacuum, so that's why there is there is nothing against the expansion process. There is nothing against the this gas expansion. So that's why in a free expansion, work done that is equal to 0. So in a first condition, we cannot use this expansion because we have nothing like intermediate stages between initial and final. In a second condition, any if we divide this process in a very slow manner, then we can get these intermediate position. But due to absence of any type of resistance against the deformation of gas, we can say that in a free expansion, work done always equal to 0. Okay, so this is all about free expansion process. Now we move again towards our slide. Okay, so we already discussed this. So in a second case, when we get these intermediate positions, then we can connect these two states with a continuous line, because now we have some intermediate position between initial and final states. In a first case, these intermediate stages are missing. That's why we connect 1 to 2 position with a dotted line. But in a both cases, we have work done is equal to 0 because expansion process is happening in a free manner. Okay. Now, free expansion, a free expansion of a gas, there is no resistance to the fluid at the system boundary as the volume of the gas increase to fill up the vacuum space. That's why work is done by a system to overcome some resistance. And since vacuum does not offer any resistance, there is no work transfer involved in free expansion, as we discussed earlier. Okay. Now we move towards heat transfer. Okay. See that what is heat transfer? We already discussed this concept in previous lectures. As we know that energy transfer due to temperature difference is known as heat. Okay, we already discussed this point. So if there is a system, this is a system, and this is boundary, and this is surrounding. Okay, so we know that heat and work both are boundary phenomena. So that's why whatever amount of Q or work that must be crosses this boundary interface, which is lie between system and surrounding. Okay, so if we want to define this heat transfer term, so what is heat? Heat, that is the energy transfer due to temperature difference. Okay, so this is the definition of heat. So if we talk about heat transfer, so that means if there is a temperature gradient between system and surrounding, suppose system having temperature something T1 and surrounding having temperature something T2, and there is no insulating layer on the boundary. So what happened? Due to this temperature difference, if T1 is greater than T2, okay, so that's why there is a temperature difference adjusting. Okay, and that's why something amount of energy is transferring from higher temperature to lower temperature, and that generates heat transfer phenomena. Okay, so heat transfer may be surrounding to system, okay, or it may be system to surrounding, okay. So if this is system to surrounding, if heat transfer from system to surrounding, that means it is, we treat like it is negative, okay. And if this heat is transferring from surrounding to system, then we treat it as positive heat transfer, okay. Like that, in a work transfer, if system done work on the system or on the surrounding, that means if work done is done by the system, so in that case W is positive, work done is positive. And if work is done on the system, then we can say W is negative. So that's all about heat transfer. And in a previous lecture, we already discussed lots of things about this point, about this topic. Now we move towards our next point, that is heat transfer, a path function. So what's the theory regarding this, that why we can say that heat transfer is a path function? So if we take again example of PV diagram, which we already discussed in our calculating work done value in a particular process, okay. So this is like that. Suppose this is PV diagram, okay, and if we want to calculate work done from 1 to second position, this is first and this is second, and this process is happening from 1 to 2. And if we want to calculate work done from 1 to 2, then what will you do? You simply calculate this area under curve, okay, and you will get work done. We already discussed this point in a previous lecture. So if we want to calculate this term, we simply say calculate PDV from 1 to 2. The necessary condition is that this process must be quasi-static process, okay. In only this condition, we can use this expression integration of PDV for calculating work transfer. And we know that work transfer W, that is inexact differential, okay, inexact differential. That's why it is not a property of system. It is not depends upon initial and final state. It's depend upon path, and that's why we can say that work is a path function. Work is a path function. That means between same initial and final condition, work may be different, because if we take 1 to 2 from this path A, 1 to 2 we're going from this path, 1 to 2 we're going this path. So WA does not equal to WB, does not equal to WC. Still, we know that here all three parts connecting same initial and final stresses, but we get different values of work which is happening through different paths between same initial and final conditions. So that's why this is all about work. Same thing is happening in the case of heat transfer, okay. In a heat transfer, if we plot temperature entropy diagram, in a 6th chapter, we discuss about this term entropy. Okay. So if we plot TS diagram for a particular process, that process happening from 1 to 2 through this part, and if we calculate area under this curve, then we get heat transfer like work transfer. So what is conclusion? Conclusion is that like work transfer, heat transfer is also an inexact differential. It is also an inexact differential like work transfer, and it is also depends upon path history. It is not a property of the system, it is depends upon path. So we can say work transfer and heat transfer both are inexact differential and both are Bondi phenomena. Both are depends upon path history. Okay, so that's all about heat transfer. Now we move towards our slide. So in this example, we can see that this is the example of work transfer. In this, we can calculate area under this curve and we get work transfer for process 1 to 2. And the same thing is happening in the case of heat transfer. If we plot this curve between T and S, here x-axis representing by perimeter X, but this is X is nothing but it is a entropy of the system. So if we calculate this area under curve, we get value of heat transfer. But the necessary condition is that this process must be happening in a very slow manner. That means this process must be quasi-static process. Okay, so that's all about heat transfer. Now we move towards next slide. So we take one example. Before discussing this question, you must know about that we use two type of energies. The first one, that is latent heat of vaporization, and the second one, that is latent heat of fusion. So if we talk about change in stage phenomena, suppose ice is melting into water or water is converting into vapor state. So in a such type of transformation of stage where solid is converted into liquid or liquid converted into vapor, in that case temperature is constant during transformation of stage. Okay, and pressure is also constant. Only on potential energy is changing. Okay, and that's why this plays a very important role to change the states, solid to liquid or liquid to gas or vice versa. So in that case we use latent heat. It may be latent heat of vaporization if a liquid to vapor or vapor to liquid transformation is taking place. It may be latent heat of fusion in case when we use this heat for ice to liquid or liquid to ice conversion phenomena. Okay, and what about if pure liquid stage is happening and temperature is changing? Suppose we have 20 degrees centigrade of water and we want to convert this 20 degrees centigrade water into 80 degrees centigrade of water. So in this case we use heat content equation, that is Q equals to mc delta T, where C, that is the specific heat. So specific heat we use there when we talk about temperature change. But if stage is changing, then we use latent heat. Okay, so now we discuss this problem. It is required to melt 5 tons per hour of iron from a charge at 15 degrees centigrade to molten metal at 1650 degrees centigrade. The melting point is 1.1535 degrees centigrade and latent heat is 270 kilojoule per kg. The specific heat is in solid state is 0.502 and in liquid state 29.90 upon atomic weight kilojoule per kg Kelvin. If an electric furnace has 70% efficiency, find the kilowatt rating needed if the density in molten state is 6,900 kg per meter cube and the bath volume is 3 times the hourly melting rate. Find the dimension of the cylinder furnace if the length to diameter ratio is 2 and the atomic weight of iron is 56. Okay, so these are the conditions which is given in this problem. So see this problem. Yes. So question is that if we summarize this problem, that it is required to melt 5 tons per hour of iron from a charge at 15 degrees centigrade to molten metal 1650 degrees centigrade. Suppose there is the iron, okay, which having mass, yeah, melting rate that is 5 tons per hour. That means 5 into 10 to power 3 kilogram per hour. That is the melting rate of iron. Okay. So we want to change this iron from 15 degrees Celsius to 1650 degrees Celsius. Okay. We want to change this iron state from 15 degree solid state to 1650 degrees Celsius liquid state. So what is phenomena? We have melting point of this iron is 1535 degree Celsius. Okay. So in this case, what happened from 15 degrees centigrade to 1535 degrees centigrade? Okay, from 15 degrees Celsius to 1535 degrees Celsius, this is a pure solid iron, pure solid. Okay, so after that, from 1535 degree solid iron will convert into 1535 liquid iron. Okay, and after that, this liquid iron 1535 degrees Celsius liquid iron convert into 1650 degrees centigrade liquid iron. Okay, so this is the phenomena. This is the first condition, this is the second condition, this is the third condition, and this is the final condition, fourth condition. So if we want to calculate how much amount of heat is needed to convert this iron from 15 degrees centigrade solid state to 1650 degree liquid state, then firstly, between 1 to 2 condition, what is 1 to 2 condition? 15 degree solid state to 1535 solid state iron, what is actual amount of heat is needed to convert this first state to second state, then we have to adopt this expression for Q solid. Okay, so what is the value of this Q solid? Q solid, that is equal to mass of iron, okay, C in a solid state, that is the specific heat of iron in a solid state. Remember that specific heat is depend upon type of state. It may be solid, or it may be liquid, or it may be vapor state. So for its same substance, specific heat may be different, because that is depend upon solid, liquid, or gaseous state. So if we talk about iron in a solid state, specific heat of iron is different in compared to same iron specific heat in a liquid state. Okay, in compared to. So if we note down this heat requirement equation, that is mc, that is specific heat in a solid state, and delta T. What is delta T? That is T2 minus T1. That means 1535 minus 50. Okay, this is. And if we talk about this interface, this is the interface second to third, in which solid is converting into liquid. Okay, so in this case, temperature is constant, pressure is constant. So that's why, as we already discussed, that during change in phase, we use latent heat. Okay, so here for this expansion, Q transforming, we use M into L, where L, that is latent heat of iron. Okay, now this iron totally convert into liquid state. Now again, we want to heat up this iron from 1535 degrees centigrade to 1650 degrees centigrade, and this all process is happening in a liquid state. So that's why we again use Q liquid, that is equal to mc liquid, that is specific heat of iron in the liquid state, multiplied by delta T, that is 1650 minus 1535 degrees centigrade. So if we calculate this term in a systematic manner, so if we adopt this equation like that, I again write this whole problem in a systematic manner. Okay, see, that is heat required to melt 1 kg of iron at 15 degrees centigrade to molten metal at 1650 degrees centigrade. So what is this amount? That is equal to Q solid, Q transferring state solid to liquid, plus Q liquid. Okay, if we put these values, these are 0.502. Here we using, we calculating amount of heat per unit mass. So we assume that mass equal to 1 kg. And after calculating this heat, we simply multiply melting rate mass. Okay, so here we consider heat required to melt 1 kg of iron. That's why we using by default m equals to 1. Okay, so don't be confused here. This is the C, specific heat in a solid state, which is given in the problem. Okay, so we're using 0.502, 1535 minus 15, plus 270. That is latent heat is given inside the problem, that is 270. M is considering 1, plus heat transfer, heat required in liquid state. Here C is a given in terms of atomic weight. In a problem, we have C in liquid state of iron, that is given as 29.93 upon atomic weight of iron. Okay, so what is atomic weight of iron? We know that is 56. Okay, so 29.90. Again, read this expression. In a problem, specific heat in a liquid state of iron is given as 29.93 upon atomic weight of iron. So that's why we use 29.90 atomic weight of iron, that is 56. Okay, so this is total C of liquid state multiplied by 1650 minus 1535. Okay, so that's all about. Now if we calculate this total value, this is equal to 1094.5 kilojoule per kg. Okay, but here we know that melting rate is given as 5 into 10 to the power 3 kg per hour. So if we want to calculate how much amount of heat is needed to convert this iron from 15 degrees centigrade to 1650 degrees centigrade liquid iron per unit time, then we have to multiply this. So the rate of heat supply required, that is equal to, mass is given 5 into 10 to the power 3. This is kilojoule per hour. If we want to convert this kilojoule per unit second, then we have to divide 3600. Now it is converting in melting rate in kilojoule per second. Okay, so for 1 kg, this is amount needed. So for that amount, which is per unit time, per unit second, is needed for melting. So multiply by this 1094.5, that is equal to 1520.1388 kilowatt. This is the amount of heat is required to process this solid iron into 1650 degrees centigrade liquid iron. Okay. Another thing is given in this problem, that furnace efficiency is 70%. Furnace efficiency is 70%. That means if this is a furnace which given heat to this iron block. Okay, what is the role of furnace? Furnace produce heat to supply this heat to iron block for processing this whole phenomena, 15 degrees centigrade to 1650 degrees centigrade liquid iron. So if we, this is an electric furnace. Electric furnace meaning we provide electric energy into furnace, and this furnace gives us heat energy. Okay, so if we provide 100 kilojoules, suppose electricity, 100 kilowatt electricity into this furnace, if this furnace 70% efficient, that means this provides us 70 kilowatt of heat. Okay, if this furnace is 80%, then it provides 80 kilowatt of heat. Okay, so what is problem? Problem is that we needed, what is the rating of furnace? That means how much electricity we have to provide this furnace to fulfill this whole process. Okay, so we know that for completing this process, we need 1520.1388 kilowatt of heat. That means this amount of heat in per unit second we need. This is our requirement to convert 15 degree centigrade iron block into 1650 degree centigrade iron block with a melting rate 5 into 10 to the power 3 kilogram per hour. Okay, so we know that requirement of heat, that means output of this furnace must be equal to 1520.13388. Okay, and in a problem this is given that this furnace is 70% efficient. So what is the Q input, that means electricity input, to operate this electric furnace? So in a which manner we calculate this? Simply we know that rating of, this is the rating, Q input, that is the rating of furnace, that is equal to rate of heat supplied, requirement upon efficiency. Okay, so what is rate of heat supply? That is 1520.1388 divided by efficiency, that is 0.7. Okay, 70%, that means efficiency what is 0.7. If we calculate this value, this is equal to rating of furnace, we get 2171.62 kilowatt. That means if we supply 2172.62 kilowatt, then we get actual amount of heat which is required to convert this iron block solid into iron block in liquid state. Okay, so this is the rating of furnace. Okay, now the question is that what is the bath volume needed? Okay, so I remove this first part. Okay, the last part is given as, question is asking that what is the length and the volume, length and the dia of bath in which this melting phenomena is happening. Okay, so here in the problem is given that volume of bath is equal to 3 times of melting rate of iron, which is given 5 into 10 to the power 3 5 into 10 to the power 3 kilogram per hour. Okay, so if we, and density is given 6900. So we know that mass equals to volume into density. So we want to calculate this volume. So what is happening? That is mass upon volume. Oh, sorry, density. That is equal to volume. So same thing is happening in this case. Here mass is given 5 into 10 to the power 3. Okay, this is a given. And since this is the volume of bath is equal to 3 times of melting rate, that's why we have to multiply by 3. But we are interested to calculate this volume. That's why we have to divide with density term 6900. Okay, so we get final value that is equal to 2.18 meter cube. Now in a problem it is a given that length to dia ratio is 2. Okay, here bath of length of bath upon dia of bath, that is equal to 2. So it is a cylindrical shape bath. That's why we simply calculate, we know that's what is cylinder volume, that is pi by 4 d square, okay, multiply by L. If we treat like a small d dia of this, that is equal to 2.18, and we put d value pi by 4, d value that is L by 2, L upon 2 whole square multiplied by L, 2.18. So after solving this expansion, we get value of L that is equal to 2.30 meter and value of D that is half, 1.15 meter. Okay, so this is the final answer of this problem. By this, we can calculate dimension of this bath in which this melting phenomena is happening. Okay, so by using this principle, you can solve all types of problem which having some stage change phenomena cases, and you can also calculate what is the actual amount of heat needed to process such type of cases in which solid is converted into liquid or liquid converted into vapor state. So this is all about work and heat transfer. And from next chapter, from next lecture, we will discuss about first law of thermodynamics. Okay, thank you very much.